This video, we're going to continue our look at double integrals, and now we're going to look at regions that are not rectangular. So we saw that using Fubini's theorem, we're integrating over a rectangular region. Doesn't really matter the order of integration. We can base the order on how difficult we think the actual antiderivatives will be, but over a rectangular, that's the simplest case, a rectangular region. Now we're going to take a look at non-rectangular regions and see how we would first define the double integrals and then carry out that process. And they're basically two standard non-rectangular regions. And let me sketch both of them and then write down the notation that we're going to use and then do some examples. So the first one, called a type 1 region, or some might refer to it as case 1, is where the x limits are constant. So remember, this is just the region that we're integrating now. This is a region in the xy plane. So let's say our x goes from a to b, and those are constants. But let's say that our y variables are not constants, and they could be functions of x. So let's say, in other words, it would be like a curve if I were to look at them, and it would normally have, when you think about it, similar to some of the area problems that we've done in previous calc classes, you might have what might be called an upper function and a lower function. So I'm just going to refer to this as y equals f of x, and let's say y equals g of x. And let's say the region now is defined by here. So hey, it looks like almost like a goldfish cracker. But anyway, so this is a region. Right? So this would be the base of our solid, no longer a rectangle. But as we saw when we visualized some of those volumes, it would still have a well-defined volume, just that the base wouldn't be a rectangle, right? It wouldn't be a rectangle. So let's see. So I'm going to use V for volume, if you will, and it's going to be a double integral. And we would start out using kind of the same notation. And let's say that our function, let's say z of x comma y, right? So this gives us the height of our solid. There's our base. We can picture a base. And then we're going to compute this double integral. Well, since the volume is still going to be a number, if you think about the process, we would want to make sure that after we've done the second integral, and when we plug in and use our standard fundamental theorem, we would get a number. Well, in order to achieve that, the last the last pair of limits that we would have to use would have to be our x limits, because these are numbers, right? X goes from some constant a to some constant b, whereas y is between the upper function and the lower function. So here's how we define, this is how we define a double integral over a type 1 region. It is the integral, and in this case we would integrate with respect to y first, because those limits are not constant. And again, let me kind of use the commonly used notation. So the g of x here would be our lower y, and then the f of x here would be the upper y. And yeah, this is how we would set it up. So this would be the lower limit on our y integral. So g of x would be down here, f of x will be up here, and then our z function is like this. So this is the function of our surface, like that, and then this would be dy. And then so if you think about this, after we evaluate this, and we're going to do the inner integral first, like we've done, we would find an antiderivative, hopefully not too difficult, and then we would plug in these this upper and this lower limit, and then we would still subtract, and what we would be left with is we wouldn't have any y's left over because these limits will be plugged in for y. So this whole inner part here is going to be in terms of x, and then you do one more integral now as x goes from a to b, and then it's like that, right? So that's the definition for a type 1 double integral, right? And type 1 is where at least one of your y limits is a variable, and then both your x limits are constants, all right? So if we think about what we've done with area, in terms of, like the area of a region, we know in some problems we can integrate with respect to x. Other problems we can integrate with respect to y. Well, that's what we would need to do if we have what's called a type 2 region. And in a type 2 region, it's the y limits that are constant, and then the x limits are your variable. So let's see what that looks like. So I'm gonna just kind of exaggerate it, but let's say that's one boundary of the region. Here's another boundary of the region. And now in terms of y, I like to use c and d when I'm using limits on the y-axis. So let's say y goes from y equals c to y equals d. Right, so those are our y limits, those are constant, and then this curve right here will be a function of a function of y, and this curve here is another function of y. So let's say this is x equals, let's say h of y, and then let's say this is x equals k of y, and the region again is between these two curves, so like this. And that's our non-rectangular region. Remember, this is just the base of our solid. And the question is, how would we set up a double integral in this case? Well, it would start out the same. You'd just say this is our region. Remember, this is our most generic way to represent a double integral. But now, again, because we want, at the end of this process, this evaluation process, we want to have a number. That means we couldn't be plugging in the x limits at the end because those are not both constants, right? So we would need to make sure that we use the y limits last, which then makes the x limits first up. So we have to use our x limits on the first integral. So it looks like this. So this again is by definition. It's going to be again one at a time. So first we're going to integrate with respect to x. Now in terms of upper and lower in the x-axis, yeah, we can't really use upper and lower because you're not the functions they're bounding the left and right of the region. So I'm not going to use upper and lower, but let's say here, so this function h of y is like the left x, right? Or you could say, yeah, so this is to the left. So this is your left. This would be your smaller because as we go to the left, x gets smaller. So this is your left x. And then this one would be the boundary on the right. So this would be your right x. And then it's always going to be your rightmost is your upper, and then, or the larger of the two, if you will, and then the leftmost is the smaller. So we would put h of y here, and then k of y here, and then again we would have the function for surface, and then now we're going to integrate with respect to x first. And when we do that, so when we integrate with respect to x and then we plug in these limits, we're going to end up with something that only has a y in there, and then we're going to integrate that with respect to y from c to d, right? And yeah, so that's the definition for working with non-rectangular regions when you have to evaluate a double integral. Okay, so let's take a look at some examples. I'm just going to use relatively simple examples here. And what I will do is I will start with a sketch of the region, show you how we can represent this as a type 1, and it'll be obvious that a type 1 will be easiest, and then do a simple evaluation to see how it works. So let's take a look at an example here of a type 1. And I'll start with sketching the region. So let's say the region is now, let's just make it a rectangular region, right? So I'm not rectangular, sorry, triangular region. So let's say this is our triangle, and then let's say x goes from 0 to 1, and then let's say that this is this line right here is just a simple line, y equals x, right? And then here's our this is our base, right? And then let's say our surface now, or z, or f of xy, if you will, the height of this surface is going to be something like, let's just make it pretty simple, 2xy, right? And we want to find the double integral of this function over this triangle. So let me just remind you of different ways that we can represent regions like this. You can obviously use inequalities to do this. So here's how we could express this region using the type 1 definition. So our triangle here represents all the ordered pairs that satisfy both of these conditions. So we know for sure that x is between 0 and 1. So I'm going to put that first, right? Because remember, in a type 1, the x limits have to be constant. Now, for the y, we can't say that y goes from 0 to 1. No, because 0 to 1 would mean that you would have a rectangle that goes up here. That's not true. The y values stop at this slanted line. So let's think about it. So the region starts from the x-axis. We know that the x-axis has the equation y equals 0. And as far as the triangle, the base is that horizontal line, but then it goes up to that slanted line. So if you notice, so I'm going to draw a couple of things so you can see in terms of like the height of the triangle, if you will. Notice it depends on which x I choose, right? If I choose an x that's close to 0, look at that the height there is pretty small. Whereas if I choose an x that's close to 1, again, it's much bigger. So these red things that I'm drawing, it just indicates that for all the ordered pairs in this triangle, the y value is always greater than or equal to 0, right? Because nothing goes below the y-axis. But then it's always less than or equal to the x, or this y, if you will. So let me write up the inequality, right? And in terms of the notation that I use, let me scroll back up just a little bit so you can see it. And I'll highlight the things. The g of x here, the lower function, is this 0. The upper function, this f of x, is this function right there. So those would be the limits for y. So we would have y goes from 0 up to x, right? So that's how you could set it up using, and remember, this is called set builder notation. So now let's evaluate this double integral. All right, so we're going to evaluate this double integral. Let me set it up generically first. So there's our surface, z equals 2xy. And now we're going to do it as in this type 1 setup. So we have, so because we're integrating over a type 1 region, the x limits have to go last, which means we're going to put our y limits first. Remember, we work inside out. and then there is our function, and then this will be dy, and then after we do this process, we're going to do another integral from 0 to 1, and then this will be dx, right? So once you have this set up, we still do that kind of iterative process where you do one integral, evaluate it using our standard approach, and then do a second integral. The difference with the non-rectangular integrals is that we can't just quite easily apply Fubini's and just switch them around, because as soon as we switch them around, we would be putting an integral with a variable limit last, and that doesn't work. That's not going to give us a number at the end of our process, right? So we can't easily, it's not that it can't be done, but we can't easily change the order of integration. So this is what we're going to do. We're going to evaluate this first, see what that looks like, and then do our second integral after that. So I'm going to do them actually separately. So we're going to do an integral from 0 to x of 2xy dy. Now remember, when we're integrating with respect to y, and this will never change, we're going to treat x as a constant. That means I can actually, because everything here is being multiplied, I can factor out a 2x. The 2 is a true constant, and the integral with respect to y means that x is treated as a constant, and it looks like that. So y dy, and then we integrate. So we have 2x. Now the antiderivative of y with respect to y is 1/2 y squared, and then we're going to evaluate this. In fact, you can put it, the square brackets around the whole thing, or just the part that has your variable, but remember, this is the y lower limit 0, and then this is the y upper limit x. And then we use our fundamental theorem. So we have 2x there. So at the upper limit, yeah, we just end up having 1/2 x squared, and then minus 1/2 0 squared. And then that simplifies to just x cubed, because the 0 squared goes away. The 1/2 times the 2, that becomes a 1. X times x squared, that's x cubed, right? So that's our value after the first integral, and now we do the second of our two integrals, integrating x cubed with respect to x. So it looks like this, and then now our limits are constant from 0 to 1, and you have x cubed dx. So another antiderivative, this time in terms of x. So this is 1/4 x to the 4th. And we go from 0 to 1. Use our fundamental theorem yet again. So we'll have 1/4 minus 0, and then this would be equal to 1/4. So I didn't give any units or anything here, but yeah, you could interpret this as a quarter cubic units of volume. That would be under this, let me highlight everything, under this surface, whatever it looks like, over this triangular region, right? And that would be its volume. So what I'm going to do is I'm going to stop this video here, and then in the next video we'll do a couple more examples, and we'll also talk about what it will look like if we needed to reverse or switch the order of integrations. Like how could we extend Fubini in a sense if we wanted to change the order when we now have variable limits. So if you're interested, hop on over and check out the next couple of videos. See you soon.